Hey everyone, ready to dive into something really cool today. We're tackling Archimedean solids.
And these aren't your boring geometry class shapes.
No way, we're talking hidden patterns, secret codes. Okay, maybe I'm getting ahead of myself.
What's fascinating is how they connect to something called close-packed spheres.
Close packed spheres.
Imagine packing oranges in a box, trying to fit them in perfectly.
Oh, okay, I get it. So it's about how things fit together in the tightest way possible, but what's that got to do with these Archimedean solids?
Those packed oranges actually reveal a hidden order. And within that order, you discover these Archimedean solids.
Wait, so you're saying there's a connection between how we pack things and these shapes? Wild. Like even the pattern on a soccer ball.
Exactly. But before we get to soccer balls, let's talk about what makes an Archimedean solid unique.
Yeah, let's break it down. What are we even looking at with these things?
Picture a bunch of polygons,
Yeah.
triangles, squares, pentagons, but all perfectly regular.
Gotcha.
An Archimedean solid combines these different polygons in a specific way to make a 3D shape, like a jigsaw puzzle. But you're building a perfect geometric pattern.
So these patterns just pop up naturally when you start packing spheres together. I need a visual on this. You're going to walk us through this, right?
Absolutely. Let's start with the cuboctahedron. It's a great example.
Cuboctahedron. Sounds kind of like a supervillain's lair, doesn't it?
Right. It's also called vector equilibrium, which sounds even more like something a supervillain would have. But it actually hints at why it's so important.
Okay, now I'm really intrigued. Tell me more about this cuboctahedron and why it's so special.
Imagine you've got one sphere, and you want to surround it with as many other spheres as possible, all touching perfectly. How many could you fit?
I don't know. A dozen, maybe?
Bingo. 12 is the magic number. Now, connect the centers of those 12 spheres.
You get a cuboctahedron.
Exactly. It's like the blueprint for this packing arrangement. 8 triangles, 6 squares, 12 vertices where the spheres touch.
So the cuboctahedron is like the VIP of sphere packing.
You could say that. It's the most basic unit in this arrangement.
Wow, we're talking about some seriously fundamental stuff here. But does this shape actually show up in the real world, or is it just a theoretical thing?
Oh, it's real. Think about crystals, the way their atoms are arranged. Often, it's a cuboctahedron. Even some viruses have that shape.
Nature's sneakier than I thought, hiding these shapes everywhere.
And the cuboctahedron is just the beginning. Remember those other shapes I mentioned? Like the truncated tetrahedron?
Yeah, the ones that sound like they need a haircut.
Exactly. And that's what we're going to do, give a geometric haircut to our Platonic solids.
Platonic solids, now you're speaking my language. Everyone loves a good Platonic solid.
Right, your classic cube, tetrahedron, those shapes where every face is the same.
I'm with you.
But things get super interesting when we truncate them, which basically means we're going to slice off some corners to reveal those hidden Archimedean solids inside.
Okay, hold on. Slicing off corners to find new shapes? I need to hear more about this truncation process. Let's take the truncated tetrahedron, for example. What's the first step in giving it this haircut?
Okay, picture your classic tetrahedron, all pointy with its triangular faces. We're going to draw lines on those triangular faces, dividing each edge into 3 equal parts, like we're marking spots on the edges.
Okay, so we're basically adding some dots to our tetrahedron. Got it. Now what?
Time for the truncation. We take an imaginary knife and slice off each corner, right at those marked spots. And this is where it gets cool. Those cuts don't just remove the corners, they transform those triangles into hexagons.
Wait a minute. So by cutting off the points, we're creating new sides? That's like geometry magic or something.
It is. And get this, where the old corners used to be, brand new triangular faces appear. That's our truncated tetrahedron. It's like finding a secret shape inside the original one.
This is blowing my mind. So we can use this truncation thing on other shapes too.
Right.
Like what happens if you give a cube a haircut?
Now you're thinking. And yes, we can apply this to other shapes, like turning an octahedron into a truncated octahedron. But the cube, well, the cube throws us a bit of a curveball.
That cube throwing a curveball. I didn't think shapes were that athletic. What makes the cube such a rebel?
Let's just say it doesn't like our usual haircut method. To make those perfect cuts, we need edges that can be divided in a specific ratio. But with the cube, we run into those pesky irrational numbers, specifically the square root of 2.
Irrational numbers. Okay, now you're bringing back memories of high school math, and not the good kind. Do we need to grab a calculator for this part?
Don't worry, no trigonometry here. Basically, that square root of 2 messes with our nice clean cuts. But there's a clever workaround using dual polyhedra.
Dual polyhedra. That sounds intense. It's like the shape has a secret twin or something.
That's a great way to think about it. Picture a cube with a light bulb inside. Now imagine the shadows of all the cube's faces projected onto a wall. Those shadows would form an octahedron. They're like two sides of the same coin, or in our case, the same geometric idea.
Okay, starting to see the connection. But how does this help us with our unruly truncated cube?
The truncated cube has a dual, too. It's called a Catalan octahedron. And thankfully, this shape plays nicely with our close-packed spheres. It's easier to build a Catalan octahedron first, and then use it to find the truncated cube.
So it's like we're taking a detour to reach our destination.
Exactly.
Yeah.
Picture a regular octahedron, which we know how to build with our spheres. To get to the Catalan octahedron, we're going to give it some headwear.
We're giving the octahedron a hat. Now, this is my kind of geometry lesson.
Exactly.
Hmm.
Imagine sticking a pyramid onto each of the octahedron's faces. These pyramids fit perfectly within our sphere arrangement.
So we've decked out our octahedron. Now what?
Now for the reveal. Remember, those dual polyhedra are like mirror images. If we find the center of each face on our Catalan octahedron, those points will line up with the corners of its dual, the truncated cube.
We found it. It's like a geometric treasure hunt inside those spheres. Who knew sphere packing could be so adventurous?
And the adventure continues. Remember that soccer ball pattern we talked about? That's a truncated icosahedron. And yes, it's hanging out in our world of spheres, too.
You're kidding, right? We can find the blueprint for a soccer ball just by packing spheres together. This is why I love these deep dives. Always learning something new.
Ready to tackle the truncated icosahedron?
Bring it on. Let's talk soccer ball geometry. Seriously, a soccer ball pattern from packing spheres. I've got to hear this.
It's all about the icosahedron, that shape with 20 triangular faces, remember?
Yeah, I remember. We're building it with our spheres, right?
Right. And when you do that, you start to see a cool pattern inside each of those triangles.
You mean like the spheres naturally make those little hexagon shapes within the triangle?
Exactly. Now picture taking two of those triangles, each with their hexagon pattern, and putting them on top of each other, but twist one a little bit.
Okay, I'm trying to picture it.
Where those hexagons overlap, boom, you get the hexagons of the truncated icosahedron.
Whoa, so we're building bigger hexagons from the smaller ones. That's wild.
And that's most of your soccer ball right there. But you're right, a soccer ball also has those pentagons.
Yeah, where did those come in? It's like a puzzle missing a piece.
That's the best part. See, when we make those bigger hexagons, it leaves gaps between them. And guess what fits perfectly in those gaps?
The pentagons, it all comes together.
It's not just a design. It's the underlying geometry of how those spheres fit together. It's incredible. We started with just packing spheres, and now we're basically designing soccer balls.
This is why I love these deep dives. But it really hits home that this isn't just about shapes, is it? It's about how everything connects.
And that's what's mind-blowing. We started with a simple idea, how to pack things efficiently, and discovered these intricate patterns, these hidden connections. It makes you wonder what other secrets are out there just waiting to be found.
That's a great question. And honestly, I'm looking at the world a little differently now. Never thought I'd say this, but I'm kind of obsessed with sphere packing.
That's the whole point. To open your mind to new ways of seeing things. Who knew geometry could be so fun?
Right. Big thanks to our expert for breaking it all down. And for everyone listening, keep exploring, keep asking questions, and we'll see you on our next deep dive.